Hi everyone, welcome to my another paper review, and today we're going to go through very deep convolutional networks for large scale image recognition. So basically the paper that introduced the VGG network, which became very popular, especially in terms of transfer learning. We're going to go through the architecture and the background and the most important information, and at the end we're going to implement it in PyTorch. So yeah, let's get into it. So the main contribution of this paper is that they used the smallest 3-on-3 convolutional filters throughout the whole network, and they increased the depth to 19 layers. And what they proved that it performs state-of-the-art results on an ImageNet, and they were second in a classification task, but they won the location task. In the introduction, they talk about AlexNet and how AlexNet revolutionized the thinking of computer vision task. So basically they utilize the GPUs and they actually use the very deep convolutional networks. So ever since the AlexNet was released, there was a number of attempts that have been made to improve the original architecture. So what they do in this paper, they basically fix other parameters of the architecture and increase the depth of the network by adding more convolutional layers. And they also use a small convolutional filters throughout the whole layers. So that's the improve they did in the AlexNet architecture. Actually, there's a lot of reference to AlexNet throughout the whole paper. And you'll see, I think even the training hyperparameters are pretty much the same. And I think it kind of shows you how important was the AlexNet paper. So let's go to the architecture straight away. And they actually trained it on 6 different architectures. The difference between them is they used different number of layers. So they did it to show you how the increased number of layers affect the output. So they start with 11 layers. They go all the way up to 19. We get 2 configuration of 11 layers and 2 configuration of 16 layers. So let me start with configuration A. So they use 11 layers, and here they use local response normalization that you probably saw in an AlexNet paper. And what they prove here is that it doesn't improve the performance and leads to increased memory consumption and computation time. So yeah, so as you can see, they use the local normalization layer after the first convolution. So how I like to think about it is each of these part is basically a block. So each block contains many layers on the top of each other. So in an A configuration we only get 1 layer, but in E configuration we get 2. And as you can see, the number of layers is increasing with each block, and also the number of the feature maps. Let me also decipher what the Con3 means. So basically it's a 3-on-3 kernel. And they also use a padding and stride 1, which keeps the size of the input. So if we pass 224 on 224 image to it, after this convolution it's going to be still 220 on 220. The only thing that downsample it is a max pool over there. So we also going to use this kind of technique, that thinking that it's a block, in our coding. So as you can see, so with each configuration they basically stack more and more layers. So at the end we've got the same configuration as in AlexNet, so FC to 3 fully connected layers with the number of classes at the end. They also use a dropout between them. So after this first convolution and second convolution, and obviously they use ReLU layers after each convolution and fully connected layers. Let me just go through more detailed information of the architecture. They use small receptive fields 3-on-3. Oh, and one thing that I haven't mentioned is in a configuration C, they use convolution with 1 kernel size. So it's basically 1 weight moving all around the image. And it's seen as a different projection of the image. So if you think about it, you can actually change the feature maps, number of the feature maps, without really affecting the input. Because in terms of if you move 3-on-3 filter, it still detects new features. But if you move just one filter, one dimension filter, so basically one value, one weight, it gives you just a different projection of the features that you already have. So let's go to the more details information. Yeah, as I said, they use 3-on-3 filters throughout the network, and they use 1-on-1, which can be seen as a linear transformation of the input channels, obviously followed by ReLU. So the convolution stride is 1, padding is also 1. So yeah, as I said, it just keeps the same dimension throughout the network, and the only thing that is downsampling is max pooling. So the max pooling they used is 2-on-2 kernel and stride 2. So later on, yeah, they have 3 fully connected layers with 1000 outputs. And there's really cool explanation why they actually use the 3-on-3 kernels rather than 7-on-7 or whatever different numbers you might think of. By using, for instance, stack of 3-on-3 convolutional layers instead of single 7-on-7 layer. So basically they have 3 ReLUs, which increase the non-linearity and makes the decision function more discriminative. So basically it increases the performance, and they decrease the number of parameters. So if you think about the kernel 3-on-3, it has 9 weights, right? So if you have 3 kernels of 9 weights, it's 27. But if you have one kernel, 7-on-7, it's 49 weights. So it's much more. I guess this configuration just speeds up a computation, and actually you can extract more features and yeah, have more non-linearity. I'll also briefly go through the training and what values they used. So they used a batch size of 256, momentum 0.9. They use obviously SGD optimizer. The weight decay, the same as I said, the hyperparameters are pretty much the same as they were in AlexNet, which not surprised me at all. So they also introduced kind of different initialization actually than the AlexNet. So they used the weights from the shallow network, so from the configuration A, and they put it in a more sophisticated one. But in the layers that they couldn't pre-initialize, they sampled the weights from a normal distribution with the zero mean and a 0.01 variance. And all the biases were initialized with 0, while in AlexNet, I guess some of them were initialized with 1. Okay, so in this paper they also used really cool techniques in terms of cropping and using different sizes of the image, and overall the paper is pretty easy to read. So if you want to give it a try, definitely you should do it. And yeah, there's plenty of cool techniques they use, the different evaluation. I'm gonna cover them here. I'm just gonna briefly go through the testing, and yeah, we can go straight into the coding. Just a few takeaways from this paper. So classification error decreases with the increased convolution depth. So that was really important. The error rate of our architecture saturates when the depth reaches 19 layers. What does it mean in basic? So it's pretty hard to achieve really better results by increasing the depth. We need to come up with something new. They also compare the shallow net with 5-on-5 filters, and they perform worse than the 3-on-3. So deep with small filters outperforms a shallow net with large filters. So yeah, as you can see, so the network with the kernel 1 perform worse than the kernel 3, and as you can see, the one with the local normalization layer, it performs worse than the one with just the one without it. So that's also interesting. I think that's it. As I said, if this is a really cool paper, if you want to read it, just give it a try. And with all that information, I guess we can go implement it in PyTorch. So I start with creating a dictionary with different configuration of the networks. I haven't put there the one with the local normalization layer or one convolution, because they perform worse than the others. So I just keep the ones with the 3-on-3 filter. So as you can see, we have the number of the layers in each block defined as an integer in the list. I think it should be pretty intuitive. So in the configuration 11, we get one layer with 64 filters. in the second block we got one layer with 128 filters, and in the third block we got two layers with 256 filters, and fourth is 2 and 512, and again 2 and 512 in a fifth layer. We're gonna create a separate block to it. We're gonna call it a block, and we're gonna pass NL module. So what we're gonna pass here is input channels, output channels, and number of layers. First we need to call super and we create a simple list of layers. So in the list we pass first convolution. So that's going to be the first block, the first layer in the block. So the first one will be, we pass in channels equal to in channels, out channels equal to out channels, and kernel size 3, stride 1, and padding 1. Also we need to define ReLU. So after each convolution or any fully connected, we're gonna use the ReLU function. So right after the convolution we got ReLU. Okay, should be fine, yeah. So then for number of layers, so this number, we will add on the top of it another layers. So for example in VGG 19, in the fourth block, we're gonna add on the top of it another 3 layers with 512 feature maps. So let me show you how we're gonna do it. So we just basically append another convolution. I'm just gonna copy this one, because the only thing we're gonna change here is the input channels. The input channel is going to be equal to out channels. So it's going to be equal to 512 basically, in our case, in our example. And yeah, we append ReLU obviously, and at the end we will add the max pooling. So the kernel size was 2 and stride 2. So we downsample the input size by 2. Okay. And at the end we're gonna create a conv, and we pass it to the sequential model. Now we just need to define the forward function, and alright, so that's it. And now we can create our VGG network. So we pass NN module, define init. So obviously we pass the input channels, output channels, so basically classes, and VGG type. So let me briefly explain what we're gonna do. So first of all, we need to define what's gonna be the input channels. What's gonna be the feature maps, sorry. So feature maps are free, so basically in channels, 64, 128, 256, and 512, 512. So basically that's the feature maps we will have, or input channels that we have throughout the whole convolutional blocks. I guess you can see it on the architecture that basically each block has certain feature maps in it. That's basically what we do here. Now we iterate over the length of VGG type. So that's the list that we have in our dictionary. Let me just also create. So that's where we're going to collect all our blocks of convolution. So convs append, and we append each block of convolutions. So we need to define the block first. So we pass the feature maps from 0. So it's going to be 3 in the first one. And as an output, it's going to be 64. Okay, and number of layers, which we take from the VGG type. Okay, I hope it makes sense for you. I will show how the network looks later on. So let me just implement the fully connected and all the other layers first, and then then I'm gonna print it all how it looks like, and hopefully it make more sense to you. So then we define fully connected layers. So the output of the convolutional operation is going to be 7 on 7 and 512. You can calculate it by basically downsampling the image 5 times by 2. So 224 downsampled 5 times by 2 is 7. So 7 on 7 times the feature maps, and then the output is going to be 496. Okay, we get 3 fully connected layers, so that's it. That's all the fully connected. We also need to define dropout 0.5 probability and ReLU. That's basically it. Then we just can pass it forward. Also, I'm going to do the initialization of the weights in here, and which I'm going to define later on. But let's start with the forward function. So we iterate basically over the whole blocks in a convs. So we get the information out of each block. So yeah, now we need to flatten it. And we are ready basically to pass it to fully connected layers. So self value, dropout, and fully connected layers. The same for the second one. And then we get the output from the fully connected layers. from the third fully connected layer. And that's basically it. We just quickly initialize weight, and yeah, we are ready to test it. So I guess they initialize it with bias 0 and with Gaussian distribution with mean 0 and standard deviation 0.01. So yeah, we iterate over the whole layers in our network, and yeah. So if layer, so basically if layer is convolution, or is fully connected layer, so and then linear, we initialize it with standard deviation, with Gaussian distribution. So this is nn init normal, and we pass the layer weights and standard deviation equal to 0.01, and we also initialize the bias with 0. Okay, think it should be it. Let's check if it works. So we will pass the 3. So the input channels are 3 because we get the RGB image, 1000 classes, and VGG type's gonna be VGG's let's say 16. Okay, now I want to print VGG modules, and we also want to see if the random values go through. So random 16, 3 on 3, 2 to 4, 2 to 4. So that's our normal input. If we would train it, that would be a normal input. So we're gonna just test it if it works at all. Well, it doesn't. Yeah, we forgot about this super. Okay. Okay, there was plenty of minor issues, which I fixed, and the code will be available on GitHub. So just in case if you're not sure about something, you can check it out, and it should work this time. Now it should work, and so yeah, that's the architecture. So as you can see, we got the blocks. So the first block, it's convolution ReLU. So yeah, one minor issue. Now it's correct. So as you recall, VGG 16, we got 2 convolution in the first block. So that's what you have. And yeah, you can see there's a convolution ReLU and the max pooling at the end, and it goes throughout the whole network. So yeah, this is how it looks like. We get the output. That's how we want it to be. And yeah, if you enjoyed this video, leave a like and hit the subscribe button. And yeah, see you in the next one.